Hey, this is Mrs. Brookshire. This is section 7.2, sample proportions, part 1. So last section we talked about sampling distributions. So we're going to make it a little more specific and talk about sample proportions. If we take a look at this, what I'm going to do is kind of look at a few of these things with you and give you a little bit of time. I would just take the time to jot down what we discussed, and then I'm going to work through some examples with you. I think that's probably the most important part. So what we have here are some different samples. So this one, if you look at it, it tells you what your proportion is from the population and then your sample size. And then these two you kind of compare because it's the same proportion and then just a different sample size to see kind of what happens here. And then same thing here, you want to sort of compare these two. This one has a proportion of 0.5, a true proportion. And this is if you're sampling size 25, true proportion 0.5, sampling size 100. And you can kind of see the difference and how the more that are in your sample, what's happening. And then this one has a little bit higher proportion and 0.9, and then sample size of 25, same thing, sample size though of 100. Okay, so I think it's interesting that when you increase your sample size, you end up, each time you end up with a normal distribution. So let's kind of look at some different aspects of these. And like I said, what I would do is I would just take the time and kind of jot these notes down. I'm just going to sort of talk you through them, and then we're actually going to work through some examples together. But if you look at the shape of these things, when n is small, so the sample size is small, and p is close to 0, that's what we have here, you've got a distribution that's skewed to the right. When n is small and p is close to 1, which is what you have here, your distribution is skewed left. You can kind of see that. And when n is small as p is close to 0.5, the shape becomes more normal. And that's what you see here. But you also notice that when n is 100, the shape is approximately normal regardless of what p is. So for each of these, you kind of see a normal shape. Okay, let's talk about the center. So the mean for each sampling distribution is equal to the population proportion. So like here, this is a sample, and the actual p was 0.1, and that is actually what you see as the center, okay, for both of those. So when you're talking about center, you do notice up here that the mean for each sampling distribution is equal to the population proportion. The reason that this is true is because p hat is an unbiased estimator of p. So whenever that's the case, this mean is going to be equal, or this is going to be equal to the actual population proportion. And the last thing I kind of want you to look at is the spread. If you multiply the sample size by 4, that's what you're doing from here to here, and here to here, and here to here. It actually cuts the standard deviation in half. Okay. And if you, so 4 would cut it in half, and if you multiply by 9, it's going to cut it into 1/3. As p gets close to 0.5, the standard deviation does get larger. So if we look at the standard deviation of these, you can see that that's happening here. And as p gets closer to 0 or 1, the standard deviation gets smaller. Okay, so take a minute and kind of look through that and jot that down. And then the next part, we're going to fill in the blank down here. So these are some important aspects of a sampling proportion. And then we're going to work through a few examples. Okay, so if you choose a simple random sample of size m, so you're sampling of size n, from a population of size capital N, with proportion p, so that's the true population proportion of successes, let p hat be the sample proportion of successes. So that's what our p hat's going to stand for, the sample proportion of successes. Then when you go to find the mean of the sampling distribution of p hat, it's actually going to be equal to, so the mean of p hat. That's what it says. So if you do all your sampling and you take the mean of your sample, it's going to be equal to the true population proportion. And the reason why that is because it is an unbiased estimator. And the standard deviation of the sampling distribution is given by this formula. So to find the standard deviation of the sampling distribution, you use this formula. Now this formula is actually, both of these formulas are on the formula sheet. And you do have to do this 10% condition. So you want to check 10n is less than or equal to capital N. Okay, so this is what we want to check. And I always check that condition first, and then I go find the standard deviation. And then the sampling distribution is approximately normal as long as the large counts condition is satisfied. So these are the two conditions that you've got to check to see if it's normal every time. So you would take the number in the sample times p and make sure that's greater than or equal to 10. And then the number in the sample times 1 minus p has to be greater than or equal to 10. So these are some things when we have a sample proportion that we're going to be checking, or that we know about it. We know that this is what the mean is. We need to check this condition, and then we can use this formula, which is on the formula sheet, to find the standard deviation of the p hat. And then this is how we can tell if it's normal. And you're like, well, why do you need to know if it's normal? Well, what we're going to end up doing on these is finding some probabilities, okay? And so when we find a probability, we want to know that we have a normal distribution. All right, so let me show you on the formula sheet where these formulas are. So this was the last chapter we used. Here was our random variable, how to find the mean and how to find the standard deviation. So this is the formula for, let's see, this was if it was, let's see, right here. So this was our formula for our binomial and our geometric distribution. All right, so this page is where we have the formula for a p hat. So the mean of p hat is equal to p, the standard deviation of p hat, there's your formula. And then we're also in part 2 going to be a difference of p hat 1 and p hat 2, and there's your formulas there. So you don't have to memorize those formulas. They are given for you on the formula sheet. So it's not on the front side with the random variables, but it's here on the back. All right, so these are the conditions. This is what we're going to know. It's a formula. We need to meet this condition to find the standard deviation, and this is how you figure out if you have a normal distribution. Okay, so here are a couple of questions you might have about those conditions. What happens if the large counts condition is ignored? If we treat p hat as approximately normal when it isn't, so the large count condition is showing that it's normal. If we treat p hat as approximately normal when it isn't, any calculation we make using a normal distribution will be flawed. So when you're going to go figure out a probability, like, hey, you know, is it, one question we're going to ask a lot of times is, hey, is it unusual for p hat to be less than whatever? Okay, well, you are going to be calculating a probability, and you need to know that you do have a normal distribution. So if you don't have that, then what you find is not going to be accurate. Do you always need the 10% condition, or sometimes need it? You need it when sampling without replacements. So the standard deviation formula assumes the observations are independent. If we sample too large, the calculated value of the standard deviation will be too large. So most of the time, we are going to go on and just do the 10% condition to make sure that that's, you know, that's met before we find the standard deviation. Okay, what we're going to do now is we're going to go through a couple of problems. So the first one says, suppose that 80% of the students at a large high school regularly use a backpack to carry their books from class to class. So that's actually our P. So I'm going to go up here and write down that P is equal to 0.84. That's our true proportion. Imagine taking a simple random sample of 100 students and calculating p hat, the proportion of students in the sample who regularly use a backpack. So the 100 is our n equals 100. So that's our sample size. So part A says, identify the mean of the sampling distribution of p hat. Okay, well that's pretty easy. If you want to know what the mean of p hat is, that's equal to p, okay? That was the first thing we wrote down on the page before. So to find the mean of p hat, so the mean of p hat is actually going to be equal to 0.84. So every time the mean of the sampling proportion distribution is going to be equal to what p is. Calculate and interpret the standard deviation of the sampling distribution of p hat. Verify that the 10% condition is met. Okay, so with the 10% condition, I'm going to kind of show you two things. Sometimes you'll see it written like n is less than or equal to 0.10 times the population. But what I usually do, I don't know why, I just think it's easier. Instead, I'll say 10n has to be less than or equal to capital N. Okay, so you want to check this 10% condition. So I'm going to go do part B right here. So instead of using this, I think this is what the book says. This is what some people do. I'll just actually, because you can actually do the math with this, because a lot of times you don't know the true population. So if I do the 10% condition, I'm going to write 10n is less than or equal to the population. Okay, so it's 10 times 100. That's my n, which is 1,000. And that would definitely be less than or equal to students in a large high school. So you want to check for that. Students in a large high school. Like a large high school is not like a Roanoke County high school. A large high school, I mean, there are high schools with 2,000, 3,000, 4,000 students in them. So we're going to assume that that's what they're talking about there. Now, once that condition's been met, we're going to use our formula, that is on the formula sheet, to find our standard deviation, okay? And the formula says, it says P1 minus P divided by N. And you just sub in. So our P is 0.84. Okay, and then I usually just do the math in my head, and 1 minus 0.84 would be 0.16. And then we're going to divide by 100. So you're going to take the square root of P times 1 minus P divided by N. And when you use your calculator, you will get 0.0367. So that is our standard deviation for our sampling distribution, which is a proportion here. Okay, so part C, it says describe the shade of the sampling distribution, justify your answer. What they want you to do here is just show that it's normal, basically. And we know from the front, to show normal, you're going to do n times p is greater than or equal to 10. And you also have to do n times 1 minus p is greater than or equal to 10. So those are the two conditions that have to be met to say that they're normal. So we have 100 times 0.84, which is 8.4, is greater than or equal to 10. And then we're going to do 100 times 0.16, because 1 minus 0.84 is 0.16, which is 16, is greater than or equal to 10. So since both of those are true, we can say that p hat is approximately normal. Is approximately. So this sampling distribution, the sample proportion is what we're going to call it, is approximately normal. All right. So in your homework, you know, you're going to start like this, then you're also going to find some probabilities. But so the mean of p hat is always equal to p. So that's easy enough. You want to check the 10% condition before you find your standard deviation. So I just do 10 times n is less than or equal to n. And don't forget that's your sample size and that's your population size. And then this is how you check for normalcy. So this is just a little proof down here. How is the sampling distribution of p hat related to the binomial count, like what you did in chapter 6? So we know when we did those binomial distributions, the mean of that random variable is equal to n times p, and this was the formula for the standard deviation. Now, the sample proportion, p hat, is the number of successes over n. So if you go and do some simple substitution in here, this is kind of the proof of how you're getting the mean of p hat and the standard deviation of p hat. We're just basically substituting in. And that's how you come up with those two formulas. So the sampling distribution of p hat is related to that binomial random variable. Okay, the last thing we're going to do here, we've got two more examples to do. Suppose that 75% of young adult internet users, 18 to 29-year-olds, watch online videos. A polling organization contacts a simple random sample of 1,000 young adult internet users and calculates the proportion p hat in the sample who watch online videos. Okay, so first of all, this is your actual p. So p is equal to 0.75. And our sample is n is equal to 1,000. Okay, so a lot of times I'll just jot that information down. Okay, number one, identify the mean of the sampling distribution of p hat. So if a sampling distribution of p hat means we would go through and we would do every possible sample and find the proportion who watch online videos. So I'm going to put this up here. So number one, the mean of p hat we know is equal to p. So in this particular problem, the mean of p hat is going to be equal to 0.75. Since it's an unbiased estimator, it's going to be equal to the true proportion. All right, number two, calculate and interpret the standard deviation of the sampling distribution of p hat. Check the 10% condition is met. Always check that 10% condition first. So it's 10n is less than or equal to the population. So 10 times 1,000 is 10,000, and that's going to be less than or equal to all 18 to 29-year-old students, or year-old, not students, but young adults. So we know that that's true. So since the 10% condition is met, to find p hat, again, I'm just going to write the formula down until we kind of get used to it. It's p and then 1 minus p over n, and it's the square root of that. So p is 0.75, so 1 minus p would be 0.25 over 1,000. And when you use your calculator and you calculate the standard deviation of the sample proportion, you get 0.0137. Okay, now it does ask us to interpret it. So let's talk about what that means. It means in simple random samples of size 1,000, the sample proportion of internet users, the sample proportion of internet users who watch online videos, will typically vary by 0.0137 from the true proportion p equals 0.75. Okay, so that would be our interpretation of the standard deviation. That's the distance away from, or the typical variation from the true proportion. So if we did simple random samples of size 1,000, the sample proportion of internet users who watch online videos will typically vary by 0.0137 from the true proportion of p equals 0.75. Okay, number three, is the sampling distribution approximately normal? Check that the large count condition is met. So again, the way that we show normal is n times p is greater than or equal to 10, and n times 1 minus p is greater than or equal to 10. So you just do some math here and you sub n is 1,000, p is 0.75, so that is equal to 750, which is greater than or equal to 10. And then you have 1,000 times 0.25, which is 250, which is greater than or equal to 10. So both of those check. Therefore, we can say that this is approximately normal. Okay, number 4, if the sample size of 9,000 rather than 1,000, how would this change the sampling distribution of p hat? Okay, well, let's see. First of all, if you increase this to 9,000, this would still be, you could go through and show, but this would still be normal. Still normal, so that would be the same. The mean would still be the same. What would change would be the standard deviation. Okay, so let's see what happens to the standard deviation if we change it. Let's think about mathematically what would happen. So instead of 1,000 here, if that was 9,000, what would that do to the standard deviation? Obviously, it's going to decrease it. It's going to make it smaller. And actually, the interesting thing is, since you're multiplying 1,000 times 9 to get 9,000, when you take the square root, you're going to actually decrease it by 1/3. So I'm going to kind of show you that. Okay. So the standard deviation would be smaller, or we could say decrease by a factor of 1/3. And mathematically, the reason why that is instead of 1,000, you'll have 9,000 here. So you're multiplying by 9, and the square root of 9 is 3. So that's mathematically how I'm getting that. But if we actually go through and we do the math here, we're going to have 0.75 times 0.25 divided by 9,000, and that's equal to 0.0046. Okay, and if you do the math, it's kind of interesting because 1/3 of 0.0137 will give us 0.0046. Okay, so you can kind of like figure that out in your head. Hopefully, mathematically, is you're multiplying 1,000 times 9, the square root of 9, so you're going to decrease it by that. If you ignore this top part stays the same, so you're decreasing it by a factor of 1/3. All right, so the last problem. So this is what we're getting to eventually. So you're gonna always have to kind of state what's the mean. You're gonna have to do the 10% condition. You're gonna have to find the standard deviation. You're gonna have to show that it's normal. And the last thing a lot of times is they're going to ask you a probability question to find the probability of something. All right, so this one kind of goes through the whole process, everything. A polling organization has a simple random sample of 1,500 first-year students, asks them, how far away their home is. Suppose 35% of all first-year students attend college within 50 miles of home. Find the probability. So here we're actually going to be finding a probability that the random sample of 1,500 students will give a result within 2 percentage points of the true value. Okay, so we're going to have to think about that in just a second. What does that mean? But the first thing I'm going to do is I know that n is equal to 1,500. That's my sample size. And I know that p is equal to 0.35. 35% of first-year students attend college within 50 miles of their home. So whenever you're going to end up doing a probability, you've got to go through and we're going to write down what the mean is because we're going to use this. So the mean of p hat would be 0.35. Okay, the next thing we're going to do is we're going to do the 10% rule. So we're going to do, and I always kind of just do like step 1. Then the next step, I always do 10n is less than or equal to capital N. And then that's going to give me 10 times 1,500, which is 15,000. But that's still going to be less than or equal to all first-year college students. So that does meet the 10% condition. Therefore, I can now go find the standard deviation, which is p, 0.35. And then 1 minus p, 0.65, divided by n, which is 1,500. Okay, so when you sub in and you find the standard deviation, you get 0.0123. So there's my standard deviation. The next thing I want to do is I want to show that we have a normal distribution here, and we know we do that by n times p is greater than or equal to 10, and n times 1 minus p is greater than or equal to 10. So n was 1500, p is 0.35. We got to show that that's greater than or equal to 10, and that's actually equal to 525, so it is. And then we also have to do 1500. So you do have to show this work. Okay, so you want to show that this is how you prove that it's normal, because they don't tell you it's normal. They don't show you an illustration. So we can say that p hat is approximately normal. Okay, so anytime you're doing a probability, you're going to go through and kind of, oh goodness, I am so sorry. You're going to go through and you're going to show what's the mean. You're going to do the 10% condition. Once you do that, you can find your standard deviation, and then you're going to show that it's normal. Now we're going to go talk about the probability. Okay, so this is kind of a weird one. It's kind of a harder one, because a lot of times it'll just say, okay, what's the probability that if you did that a student that 25% of the students, or less than 25%, live 50 miles from home. So this one's a little different because it's asking you what's the probability that you're within 2 percentage points of the true value. Okay, so we need to think about what that is. So if the true value is 0.35, 2 percentage points would be 0.33 on this side and 0.37 on this side. So this is what we're trying to prove here. Is what's the probability that p hat will be between 0.33 and 0.37. Okay, so what we would do is we normally draw out our normal distribution. Okay, and in the middle we have our mean, which is 0.35, and we're trying to figure out 0.33 to 0.37. So I'm going to shade that. Now, the way that I have done this, I guess every teacher does this a little bit differently, but I just use technology. So I'm going to write out norm CDF if I'm trying to find that probability. I know we have a normal distribution, and my lower bound is 0.33. Need a label. My upper bound is 0.37. My mean is 0.35. And my standard deviation we found is 0.0123. So I'm going to use my calculator, and I'm going to go through, and I'm going to use technology. Make sure if you do, you need to label everything. And when I find that probability is 0.8961. Now I know some of you guys have done z-scores, and then if you did a z-score, you would find that, and then for each of these, and that would be your lower and upper bound. And if you use a z-score, you would use 0 and 1 here. So I'm going to kind of conclude this, and then we will be finished with this first section of 7-2. So that's really about 90%. So about 90% of all samples, SRS is of 1,000. 1,500, not 1,000. Sorry about that. Students give a result within, so I'm sort of answering 2 percentage points is the question of the true population. Okay? So again, when you're going through and they ask you the probability of something, this one was kind of odd. We kind of really had to figure out like what it is. What is the question that they're asking on this one? But anytime you're finding a probability on a sample proportion, you want to go through and you want to state the mean, do the 10% condition, find the standard deviation, show that it's normal, and now that it's normal, we can use our normal CDF to figure out the probability. All right, the next section is going to deal with the difference of two proportions.